the boat.
Can I talk?
Yeah.
So perfect. So you agree that even if I use the telescope to magnify it, right? If the ship went down the geometric horizon, magnification won't bring back the missing part, the missing lower
No,
portion.
no.
No,
So
you
this
don't
is
agree
what
that
T-Dub. This is what
because that's
T-Dub post. This is what T-Dub posted.
that's tested.
Even zooming out, changing the size of the aperture compared to the human eye and a telescope. You will lose resolution of the boat first on the horizon if you're just using your eyes. And then you get a telescope out and then you can see the boat again. And then it will keep sailing away and you'll lose resolution of it. And then you'll get a better telescope out and you'll see the boat again until it goes
It
away.
won't bring back the missing lower part though.
Okay. It won't bring what? Back the missing boat? Let me
No,
point
the
this out
missing
to let me
lower
point this out
portion.
to you. Let me
Missing
point
lower
this out to
portion.
you. Let me point this out to you. I can see
Whoa.
boats 23 miles away across the English Channel. I
Huh?
shouldn't be able to see boats across the English Channel if the Earth was a sphere. I can watch boats sailing from England to France. I've been on the boats and I've watched France come towards me and England go away, but never lose sight of either. You're telling me what in your imagination or in one just observation. I'm trying to point out to you, if you change the optic, the boat is still there. That's
The
a
boat is
problem
still there.
because there's a limitation if the Earth was a sphere.
The lower part is hidden though.
Yes, the lower part is hidden. That could be due to the atmospheric conditions. The
What
boat could be
atmospheric
20
conditions?
miles away and I can't see the bottom of it. But if I'm at 6 foot, I should have started to lose sight of it at 3. And at 20 miles, I shouldn't see the boat anymore.
Okay.
I mean, can I
Yeah.
interject?
Yeah.
Can I?
Yeah.
Hello?
Yeah,
We've
go
said
ahead.
yes like 3 times now.
Wait, am I audible?
They've
Well,
said
it
you can
sounds like you can't
interject
hear
3
us, so
times,
I
4
don't know.
times now. Please get on with it. Come on.
Okay, that's amazing. So, what Sonic can actually do is basically like, yes, you can concede to the idea that synchron reflection can exist, and yes, there is like a temperature and density gradient within the atmosphere. But however, the burden is upon you to prove like how does that actually like replicate the observation. We can just simply say that there is a physical
I tell you.
horizon, there is
I tell
curvature,
you.
and there is geometric horizon that
I
exists.
tell you.
And what synchron reflection really does is basically make an apparent horizon on which we can observe from geometric horizon.
Sinking refraction is the object sinking, right? Not the horizon itself. The horizon doesn't sink. The
Sinking
object appears to
refraction.
sink. Do you require citation? Second of all, how do we falsify and validate this? By equivocating it to the predictions of the sphere, which is giving us a calculation. If we're making an observation at eye height, there's going to be a prediction of the boat at distance where we can lose sight of it. The geometric horizon is 1.225 multiplied by the square root of the observer's eye height in feet, which is where we get a distance of an approximate horizon about 3 miles for a 6 foot observer standing at the
Where do you get the
beach.
calculations from?
A radius with 3,959 miles.
Okay, so when you made the claim that you're supposed to see an object around an X amount of miles or meters, like where do you base your calculations from? Is it because of geometric horizon?
That makes the prediction of when we should lose sight of the boat.
No, it
Remember,
doesn't.
our friend earlier was saying, I can't see the bottom of the boat because that's the curvature of the Earth.
Look, if you go on Google and type in like horizon calculator, you may find out that within their note it say relying on geometric horizon alone using just mathematical calculation is basically flawed because it does not take into account that there is a density gradient that happened in the air, which
Absolutely.
actually
Absolutely. So we can add about 16% if we're going to use some kind of refraction model, either terrestrial refraction, 7/6R, and we can compare a calculator where we slide refraction along. We won't actually be bending the light, we'll just be making the Earth look bigger. in some refraction models, right?
Okay.
So
That's
we
beautiful.
can take that into account. So let's take, for an example, an observation I'll put into the side chat in a moment, where we should have a horizon at 3.5 miles, but it's at more than 10 miles. If I was to give you refraction with the extra 16%, that's going to give you a distance of 4 miles, not 10 miles. So I can give you refraction, but the observation always supersedes your type of refraction. Also, refraction requires specific requirements in the atmosphere, density gradients and so on. And as within the refractors indices of light
Actually,
tends
to
to
find the
deviate
function of
towards the
the
denser
entity.
medium, which is generally upwards.
No, actually, like for you to actually find the path of the light, like you need to find the function of density in respect to air pressure and temperature. But either way,
Mm-hmm.
the crux of this whole discussion is that you
Well, we
provided
can
an
measure it.
alternative. Okay, you provided like an alternative explanation as to how things.
Well, we measure it though, don't we?
No.
That's why light has a different
No.
refractive indices depending on the wavelength that it has.
Okay, can I finish?
I thought you said that we couldn't. I was just pointing out that we measure it.
Can I finish?
Yeah, sure. Sorry, you're just boring.
That's amazing. But the crux of the discussion is that you provided alternative explanation as to how ships actually disappearing bottom up. We're not asking whether if the ship gets smaller as you go further, or you get smaller due to refraction or sinking refraction. Sinking refraction does not make ships disappear bottom up.
What's sinking then?
Yeah, it does.
Sorry, I do apologise for interrupting, but what are we talking about sinking for then? What is sinking in relation to what?
Are you appealing to definition of sinking?
At the moment, if we're talking about atmospheric refraction, there's about 5 different types of it. Right, this one's sinking. There are other ones like looming. Right, it also comes into the categories of mirage, inferior and superior, all having specific conditions that deviate the path of light. When we're talking about sinking, that's an object in relation to the horizon that looks like it's sinking. The reason why it looks like it's sinking is because we can't see the bottom of the object. I'm appealing to definition because we're talking about the deviation of light. This would fall into that category of why I can't see the bottom of that boat. It looks like it's sinking.
No, even the phenomena even the phenomena itself. Even in the phenomena itself, the sinking refraction.
Do you want to hear it? Do you want to hear it from an expert? Do you want to hear it from an expert in optics of the atmosphere? No, you can't. Young, Andrew Thomas T. Andrew T. Young. Andrew.
Yes, I can finish.
Young. Andrew T. Yeah, I'm just going to cut you off, mate. I'm going to cut you off
by saying.
Yeah, I'm going to mute you and then read over the top of you.
Explain an observation, which can also.
Right. I'm going to read this out to you because you need to hear it, right? Make sure you don't deafen yourself in protest of being muted. Young, Andrew T., 1994, Optics of the Atmosphere, reports on progress in physics, right? Shows the page numbers. Atmospheric refraction can bend light rays such that distant objects are displaced vertically, causing parts of these objects to drop below the apparent horizon or become partially obstructed, even though the line of sight is geometrically unobstructed. This effect results from vertical refractive index gradients near the surface that produce curved ray paths. Now I'll unmute you, and you can try and refute Andrew Thomas Young, somebody from your own side.
Oh, that's really amazing. I already conceded to the idea that the light can be bent due to atmosphere, by the way, as I have discussed with Jedi, due to the atmospheric refractive index that can be under density gradient.
Causing apparent bottom-up obstruction.
But the thing is, this phenomena, which is like ships disappearing bottom up, can also be replicated in regardless of the density gradient of the atmosphere. It can happen either way. The difference.
So how do you know when it is and isn't happening then?
One can happen farther than expected. The other
Okay, so how do you know? How do you know the cause? Then? How do you know the cause?
Either way,
how do you know what's causing the visual effect?
I'm not asking as to how far does the ship disappear or how small does the ship disappear, but rather my question is, why is it the case that the ship disappeared bottom up?
We've just told you.
Oh my god!
Because it's not always 100% of the time that this occurs. The boat appearing to disappear from the bottom up.
Always, by the way,
it isn't, dude.
It does always, by the way. Eventually,
no, it doesn't, dude.
Yes, it does.
Light deviates depending on the gradient. If that gradient isn't met, the light isn't deviate. If it's equal surface temperature to atmospheric temperature and there's no gradient, guess what? No deviation of the light.